Hello. If you have a stone tied to a rope, you can swing it at whatever speed you want, right? If you swing it faster, the tension in the rope will just increase to provide you with the required centripetal force. Now, if you have a satellite orbiting at some particular altitude, can you have your satellite moving at whatever speed you want? Okay, are you aware that a satellite in orbit is actually unpowered? So to park a satellite actually means two things. First, you must use your rockets to bring your satellites to the altitude that you want. You must make sure that you leave the satellites there with some particular speed. And then after that, you just switch off your engine and the satellite will automatically go into a uniform circular motion. So the math is really quite easy. It's the Earth's gravitational pull that provides the required centripetal force. So we can equate gm over r squared to mv squared over r. The mass of the satellite, little m, gets cancelled, rearrange, and then you get v is equals to square root of gm over r. So firstly, notice that the mass of the satellite is irrelevant. So when we calculate orbital speeds, you don't have to provide me with the mass of the satellite. Next, this expression clearly shows us that the orbital speed decreases with orbital radius. And for a particular r, there's a particular v. Now, what about the orbital period, which is the time taken for the satellites to complete one orbit? Now, that can be calculated quite easily. It's just distance divided by speed. So the circumference of the orbit divided by the orbital speed. Then you get this expression. So what does this tell us? That the orbital period increases with orbital radius. And for a particular orbital period, there is a particular orbital radius. This graph shows how the orbital speed varies with orbital radius. So clearly, the orbital speed decreases with orbital radius. RE is the radius of the Earth. So all the satellites which are orbiting just above the Earth's surface, those with altitudes of about a few hundred kilometers, they all require an orbital speed of about 7.7 kilometers per second. Those that are orbiting at higher altitudes like 20,000 kilometers or 36,000 kilometers, those will have lower orbital speeds. This graph shows how the orbital period varies with orbital radius. So clearly the orbital period increases with orbital radius. All the satellites which are orbiting just above the Earth's surface have an orbital period of around 1.5 hours. Can you imagine going around the Earth in just 90 minutes? Now, if for some reason you want your satellite to have an orbital period of 24 hours, then you have no choice but to bring your satellite all the way from the surface of the Earth all the way to 36,000 kilometers above the Earth's surface. Only at this altitude will you have an orbital period of 24 hours. Now remember, it's all because we are relying on the Earth's gravitational pull to provide us with the required centripetal force. Because of that, at a particular r, there's only a particular v which satisfies this equation. And it's good to have the results in your head that those that are orbiting nearer to the surface of the Earth will always orbit at a higher orbital speed. And those that are orbiting further away will always have a longer orbital period. That's all. Ta-ta!